Yeah, I'm Shinan. I'm in my final year, and I'm very fortunate to be advised by Professor Nick, and I also work with Professor Francesco Forzino, who is also originally from WINLAB. So that's why I have a chance to visit here. And yeah, thank you all for coming. Thank you, Anne, for introduction and also hosting me for this seminar. Today I'll be talking about connected machine intelligence in operations. So this talk summarizes my recent endeavors on making ML practical for many networking management tasks and also networking security tasks. So feel free to ask me questions during the talk, and we can answer it in the middle. But because of time issue, maybe we can leave more questions in the end. We can ask like more of these like clarification questions in the middle. Yeah. So today we're seeing machine learning models becoming more powerful, and they are increasingly used in networking tasks. For example, there are network forecasting service providers like Verizon. They need to predict user demand in order to adjust their network capacity. Essentially, they need to have complex time series machine learning models to do that work. Also, many ML-based traffic analytics work. We have some systems to do service recognition, intrusion detection, or even quality of experience measurement. Yeah. So essentially, because network traffic are getting more and more encrypted, in order to get some insights from this, we need to have some classification models to be applied to the different workflows. Even for applications like activity recognition, people can use network traffic to infer behavioral patterns of daily users, sleep stages, and access. A typical ML pipeline in networks is not very different from other many domains. So for example, we have this historical network data set. We try to featureize it into the best approaches, and then we train our own model. During deployment, we will have this the same model being deployed and facing this online network data. Oh, why am I disconnected from Zoom? Wait a second, sorry.
What happened? You lost Zoom?
Yeah, I think Zoom, I just got disconnected there. But now I'm back. So this pipeline is simple, but it's not really working in many networking scenarios. Why is that? Essentially, we are facing a lot of practical challenges to apply machine learning inside networks. There are a few to name them. The first challenge is this accessibility to high-quality labeled data sets inside networks. Essentially, we as a community, we do not have an equivalent as an ImageNet as in computer vision community. There are some open source data sets out there, but they are often pretty old and there are many tech companies who got a lot of data, but they are not willing to share them because of customer privacy, and they don't want people to analyze the internal system. As a result, like we don't have enough accessibility to high quality data. And how about we find a way to augment this data set ourselves? The next challenge that I see is this very huge model inference workload. Essentially, when people are doing this task, it's often, for example, on like a core network or some enterprise ingress and egress data. And that workload can be up to tens of gigs per second or even hundreds of gigs per second. Still, we want to assign label to each and every network traffic. In this workload, there's no previous systems built for that. So we actually leverage multiple models together for a collaborative service. The third challenge I see is because of networks are evolving systems. Essentially, the network you are seeing today might not be like the network you are seeing tomorrow. So for machine learning, it's very data-driven. But as time goes by, we may see like inside the network, the data patterns become shifted. We have hardware being replaced, have like software being upgraded. Essentially, like all these data distributions change. We need to find a way to monitor these like changes or results, and also reason about why that's happening. And then later we can update the data for us to update the model further. So for my research, I'm really trying to deal with these three different challenges. I have two major threats. One is this operational ML for networking. Another is like I apply the lessons I learned to build scalable and efficient systems to some digital well-being and security tasks. To deal with challenge one, I explored using, for example, Gen AI techniques to get a synthetic network traces. And these are interesting work, but I won't talk about them in detail. To deal with the second like challenge, we have like this huge workload to deal with. So we built several like ML-based traffic analysis systems, and I will talk about one of it as our main dish today. To deal with this model decay over time problem, we collaborate with Verizon, and we are deploying in their like networks on the concept of solution. I also did other work on applying network traffic analysis techniques to more like human health or well-being tasks, such as in-home activity recognition and privacy. I also did some kind of work on like wireless, some network service, attack and defense. Recently, I'm interested in more like the language model and web service. How do we measure their vulnerability? So all these are like topics that I've been doing, but I'll mainly talk about two stuff in red. If you are interested in other like topics, just feel free to approach me. I am here the whole afternoon. So yeah, feel free to talk to me more about it. For today's content, I'll be trying to answer these two questions. The first is that how to make accurate and efficient model system co-design for network traffic analysis. Then later, we want to connect network models with other modalities, maybe for well-being purposes.
Hold on a second before you continue.
Sure.
The previous one.
Yeah.
You said that the problem is that the network is changing, so we have trained the system for a specific architecture. If the architecture changes, then how did you solve this problem in your previous work?
Oh, you mean here, like the third challenge?
Yeah.
Yeah. We
Just
today I will be
one sentence summary.
Right.
What was the approach?
The approach is to look at the input and output of a model and trying to distinguish like when patterns getting changed, we want to detect it, and we want to associate certain reasons why this is getting changed. And because of this explanation, we can mitigate it on the model. It's like we're constantly adding patches to like the models when we detect the getting wrong.
So basically, you
update the system. Right. Yeah, it's updating the models frequently based on a lot of reasons. Yeah. And I won't talk about this in detail today, but if you're interested, we can take it off to offline discussion.
Okay. Thank you.
Great. So yeah, let's head into this first question. I'll be talking about ServeFlow. It's a real-time system, and we found some very interesting dynamics of model system co-design, and we want to co-optimize this. It's called a fast-flow model architecture for network traffic analysis. Yeah. In network traffic analysis, we're seeing this like complex ML models being applied, and they often have pretty high requirements. In such tasks, each of these incoming traffic flows is issued a label by an ML model. For example, service recognition. We're trying to identify whether this flow is from Zoom traffic, YouTube traffic, or web browsing traffic. Essentially, these like insights to help us to have like a better flow prioritization technique, have a fair bandwidth allocation to this flow. Another example is device identification. Yeah. If I'm an ISP sitting on like a core network, I just have no idea what device these flows are coming from. But there are many devices with vulnerabilities. They might be like compromised, if we can have some recognition of device types, we can essentially build like a better firewall. Even for quality experience measurement, QoE metrics are often gapped from like application layer protocols, but they are more and more encrypted as payloads inside like transport layer or network layer packets. So it's very hard for us to get access to those. How about we get all these metrics from network layer or transport layer features? These classifications are pretty essential for network management or security purposes, but they require fast reaction time. Yeah, for example, for flow prioritization, service recognition needs to happen in real time with a requirement of under 50 milliseconds of like action time. So also you need to like deal with this very high throughput problem inside like enterprise network. Here we have a typical ML-based network traffic analysis, especially on the inference side. Yeah, system, and it also contains like 3 stages. So in such a like system, let's say you have first is flow collection phase. Yeah, people need to wait for enough context or just like enough packets to come before they can like do something else. Then if they collected enough information, they'll start to do some featureization on it, getting flow-based statistics, or they have like this raw header field base. And then they will be put into models for inferences. There are a lot of like existing serving pipelines out there, not designed for networking, but for like other machine learning tasks. For example, torch serve, like TensorFlow, they also get their serving pipeline. Yeah, they are designed to decrease the inference cost. For a lot of non-networking tasks, the bottleneck is in the model computation. We are seeing a trend that models becoming larger and larger. For example, language models, they have to sit across tens of GPUs in order to be used. But their input are actually a lot smaller. Yeah, like oftentimes, even for now, the biggest input might be just 10 million tokens, which is oftentimes just like 10, 20 MB in total. Yeah, so that's not a lot. So it makes sense that people are trying to optimize for like a lower inference cost using model pruning, quantization, knowledge distillation, or running it on specialized hardware like GPU. For networking tasks though, this workload is very inverse. We have much more models to handle this task, and they can do pretty well, at least on the task I already described. Yeah, sometimes we're seeing like gradient boosting machine is better than deep neural network. Yeah, but the input, like we have a super large streaming input, essentially it can be like tens or hundreds of gigs per second. Still, a lot of people are following like the path in non-networking scenarios. They are doing efficient modeling, feature selection, running on specialized hardware for this model inference workload to get it smaller. Oftentimes, they need to wait for 4 to 100 packets, or even like the entire flow before they can make an inference. We look at this pipeline and we take one step back. We ask ourselves one question. Is it really the model inference cost the largest bottleneck in network traffic analysis? Indeed, there are reasons why people are using more context, because that just increases the model performance. For example, for 11 class service recognition tasks, essentially, when we are adding more packets as features inside our model, we're getting a higher F1 score, which means like better model performance across multiple different types of models. But is it really worth it to wait for more packets to be collected? Surprisingly, we found that no, the packet waiting time is actually a lot higher than the actual inference time. So here on the left side, we have this CDF, a flow collection time. And in order to wait for the second packet to come, the median latency we need to have is often already like tens of milliseconds. in order to wait for the 10 packet to come, oftentimes we need to wait for like thousands of milliseconds here. And it can be as large as 10 to the power 6 on the waiting time. For inference time though, they are in the same scale. They are all in a millisecond. Here is our feature computation time. Here is all like the model's actual inference time. And surprisingly, we see that if after we get one packet and we make an inference on it, maybe use a multi-efficient model, they are in the scale of the 10 to the power of -2, which means that there is a big opportunity for us. After we get the first packet of the flow, we make a prediction on it, and then still we need to wait for a very long time until other packets to come. So how about we take this as an opportunity?
What is LGBM?
There's a light gradient boosting machine. It's
what?
Light gradient boosting machine. It's one of the machine learning models we use here, and it's quite performant.
It is decision trees. What is it stand for?
So decision tree and convolutional neural. Yeah. Go ahead.
Is packet waiting time depends on the application? So for example, like video download versus like short videos, and also regarding the networking, like if you use different network, it varies a lot.
Yeah. So this like packet waiting time is mainly for the applications I mentioned in the intro part of it. The inter-arrival time somewhat bounded by their like round trip time. This round trip time sometimes is people all use this before. Okay? So it's often 10 milliseconds or even more. So compared to like the several microseconds of actual inference time, it's actually a lot less on this side. Good. Another observation we have is that even for the first packet inference, we're seeing that this inference time across different models can differ really largely. For service recognition, we have multiple models, and this one is random forest. This is another gradient boosting machine. And here we have the S1 score versus their latency. The deeper green means they have better model performance. The deeper, this is blue. The deeper blue means they have like a better latency. And we're seeing that like this light GBM, it has a bad model performance, but it's not necessarily the slowest. And decision tree, it's a fastest, but it also got a okay result. With this observation, we found that there's a very interesting surface for us to optimize on between this like F1 versus inference time. This holds true across multiple different applications, such as device identification, as well as this conferencing app to email. Given these two observations, can we design a better system by solving these right bottlenecks? We want to get like a comparable result as well, like especially on the model performance side, as what people are used to do. But we also want to improve on the end-to-end latency, as well as having like a higher service rate. Is that really possible? The answer is yes. That's why I introduced this fast-low model architecture. So the idea is that we want to optimize the balance between speed and accuracy. On the one end of the spectrum, we have gigantic model, maybe not gigantic, but more complex model architecture that waits for the optimal number of packets to come, and then it should give us the best result. On the other hand of the spectrum, we have the quickest model with an okay result, but only waits for one packet. How about we use this fast model as a filter? We let all the traffic to pass through the fast model first and get a label. Then we try to like measure whether we're satisfied with the result or not. If not, we'll be putting that into like a more accurate analysis, a slow model. You may wonder why would this be beneficial? Because this is like a offloading mechanism. A lot of this previously more expensive operation will not be served by this fast model alone. So it avoids waiting for more packets to come or more inference time from different more powerful models. When would this be beneficial? This is also quite interesting. When we're seeing there's a significant disparity between two models, and they have different operational costs, and they also have different performance. The design ServeFlow incorporates two fast flow disparity. It takes two opportunities to employ this architecture. It optimizes on both this first packet inference time and also the flow collection time. So here we have massive traffic coming in, and we will have a feature extractor. All the first packet of feature will be put into Q1. Then it is dealt with by this fastest model using the first packet, which is oftentimes a decision tree. Later, if we're not satisfied with it, we're sending all the flow keys inside the batch model using the first packet. This is still pretty fast. And even after these two models inferences, all the time we're still waiting for more packets to come. So that is our second opportunity, this flow collection time. For the second to n packet features, we'll be putting it into Q2 when it comes and cross-check with the flow keys that we're not satisfied with, and put it into this good old full packet flow model for any inference. So essentially, we're doing two times of filtering here and here, and then the workload arrived at the heap will be a lot less. Actually, 75% on this real world data set we already do. Yeah. Another benefit for us to employ this queuing design is that we now have this a stable traffic management system. Yeah. So this massive worker is essentially a queue, and we have some complex designs into it, and basically these features can now be sent into different types of CPU, GPU with different specified number of cores. Yeah. So it also achieves parallelism. You may wonder, how would a user interact with ServeFlow? We are trying to make it very usable, especially for network operators as well as graduate researchers. So ServeFlow extracts inference features, which is essentially full header field bed, using ServeFlow Hub, which is a lot faster than the previous implementations of this. And it does all the dirty work for you. Users can then train models in their favorite Python library. So essentially, you don't have to rely on a very complicated domain-specific languages. Instead, you can just train whatever you like with Torch, TensorFlow, GBM, this type of different model architecture. So it supports all of this type of models. Yeah, then users need to specify a single inference task with 10 lines of code and specify also the number of hardware they're going to use. ServeFlow then changes all the models into the same model format, which is Microsoft Onyx, and then it will be deployed across heterogeneous hardware with any number of consumers being specified using C++ or Python, depending on what kind of workload or kind of environment you want to choose. There are a lot of work that may be trying to serve machine learning models under a higher rate, right? They offload a lot of stuff on the smart net. But essentially, those type of work, the model architectures they can support is far less compared to this type of approach. We are basically trying to use some commodity hardware, commodity computing units for us to be using a machine learning network traffic analysis task. So there's still one very critical question remains unanswered, that how do we know what type of flow classification request should be sent from a fast model to a slow model? That's why we designed two different types of flow assignment algorithms. The idea is that without any ground truth, actually we cannot get any ground truth under that line speed, like 40 gig per second. ServeFlow wants to evaluate the likelihood of fast model prediction being good enough. So what do? The secret sauce here is uncertainty. Instead of let the fast model directly give us the label, we let it output the probability vector. And basically then we take like an entropy, compute the entropy of the probability vector. Then we kind of know how confident the fast model prediction is. The second algorithm is the flow-based per-class uncertainty threshold. This is based on intuition that some classification models are better at detecting some classes. So basically, we don't want to take the same threshold for different classes. Essentially, they need to have like a validation set, like try to get some similar workflows. And then we will calculate the portion. And the intuition is that when we are assigning the fast model's prediction, or like this request to the slow model, we want to assign the largest chunk of incorrect prediction so that later the slow model can help you correct it. Good. So these are the designs. Do you have any questions for all the designs here? If not, let's go to you. Do some evaluations on this. Basically, here we have two baselines. One is called best effort. Essentially, we will have immediate predictions after features being extracted. All steps are being implemented in C++. So it should be the quickest. There's no step inside them to make it slower. The next baseline is called the queuing design. When the traffic comes much faster than the model inference speed, like one way is to do like best effort just to discard it when it's exceeding the capacity. Another is to have a queue to have like a FIFO management of these features. Yeah, they can be either in the ran or row. For this, that queuing is essentially ServeFlow without fast flow and assignment algorithm. Good. From a latency perspective, yeah, also keep in mind that like ServeFlow can achieve what like a traditional model, the slow model can achieve on the accuracy side, and still it can accelerate 76% of services of flows to milliseconds level. So let's look at it. Compared to queuing and also like best effort, queuing at this like speed is already congested. So you will see a lot of like super long tails. This like 10 to the power 4 milliseconds. It's just like several seconds already. Yeah, it's not all we want. And for back effort, you can see a lot of times because they have to wait for 10 packs to come. So it's actually have a very long like time waiting for it. For ServeFlow, you can see like at least like 76% of these flows are being brought down a lot. We compress the time into. What is the CDF? You mean what is CDF short for? Yeah. Cumulative distribution figure. Yeah. And this is the end-to-end latency. So it basically shows like the distribution of like the accumulation of this distribution. Oh, well, let's break it down for different stages. And we have collection, feature compute, queuing, inference, and also end-to-end. And ServeFlow here, you can see this packet collection time is becoming minimal because a flow starts when we collect the first packet. So the collection time is not a lot. And also the feature compute time here, because for the other two baselines, they have to compute like the features for 10 packets or even more. But here we only need to collect compute it for 1 packet for the majority of the traffic. Yeah. So you can see ServeFlow is bounded by this queuing time, which is the like price we have to pay by implementing something like a complex queuing mechanism. for example, this queuing baseline is also bounded by the queue because it's just congested in the queue. For the best effort, you can see it's bounded by this data collection time here. Yeah, that's mainly because like we need to wait for packets to come in order to collect them. How about scalability? ServeFlow is able to scale it up to the level of like CD network backbone using a just 16-core CPU server. So here is the number of consumers we're adding. By consumers, here we mean like how many cores of CPU here. Yeah. And essentially, the largest we can achieve is almost like 50K new flows per second. Yeah, because for each flow, we need to only do like a prediction once. So it's actually like some flows are very long. So combining together, this is matching like the rate of maybe like 40 gigs per second. So, and remember, this only happens on like a single 16-core CPU. Yeah. Go ahead.
Increase the number of people kind of converging to that too, or would it continue?
Yeah, that's a good question. I would say like maybe when it's like long enough, it will be achieving like some kind of level. Yeah, but yeah, at least we're showing that this is already sufficient for like a CD network platform. But like because like the CD network, they are also increasing. Yeah, so essentially we want to make it this faster. Maybe by that time we have a ServeFlow plus another version to solve it. Hopefully, yeah. So and this figure evaluates like the assignment algorithm. Essentially, it is able to achieve like only assigning 24%, and we get the same result as we are running everything using a slow model. This point is running everything using a fast model, and our goal is to push this line to as left up as possible. Yeah, and you can see that compared to like the random baseline, it means like how like we just randomly sample from like a uniform distribution on all the requests. Yeah, and we will send like randomly to the slow model. You can see it's like having this linear addition on this S1 score. But for ServeFlow, we can actually put already achieve like the same result as a slow model pretty early on. Here we have Oracle as another. It's not baseline, it's just like the upper bound. And Oracle means that when we are deciding which flow to send to the slow model, we are relying on the ground truth. It means that we always prioritize this assignment of incorrect predictions to the slow model. Yeah. There's an interesting uphill here, and then it drops back. It's mainly because that like the fast model sometimes can make correct predictions, but they like the slow model might disagree with it. So that when we're assigning everything to the slow model, it will just drift back to like a slow model performance. This Oracle line is super interesting. It's an indication that even though we have the best way of like doing this assignment, the best approach is not to send everything into a slow model. The best approach is to send the least amount of flows to a slow model so that we can achieve a better F1 score and also a lower latency. Okay. Any questions about this?
Yeah, I have a quick one. Can you hear me?
Yeah.
Yeah. Do you look at a packet body or only packet header?
It's only the header because everything we discussed here today is that the payloads are encrypted. Yeah. So all the header field bits are the features we're taking into consideration here. Basically, the network layer and like the transport layer features.
Okay, so layer 2 and layer 3 is it, or layer is that right?
Yeah. Yeah.
Okay. All right. Thank you.
Good. So for some takeaways of this work, essentially ServeFlow is a scale system, it can be running across heterogeneous hardware, and it achieves all the good stuff. Yeah. And the key bottleneck we have here is this flow collection time, maybe packet waiting time. Yeah, and we developed a novel flexible model architecture to deal with that. Uncertainty is a very interesting and great metric, but you have a low overhead on computing the whether this model is confident enough on their prediction. So it can be a very good metric for us to decide which request to assign to the flow model. Okay.
Question. So the flow model always takes a fixed number of packets, right?
Yeah, in our design, we will have like a profiler on how many packets are like enough for or like the best performance. So we have the assumption that the flow model is always like the model that give you the best result. And from that, we will have like a fixed number of packets input into it. Yeah, but I get what you're saying. Like essentially, we can make it more adaptive depending on different workflow. Yeah, that is actually the idea of one of my other paper. We can discuss maybe more about it in detail later. Cool. And the next question is basically like I will answer it in maybe 10 minutes. This is not a very large paper or long paper, but I'll talk about it. So now that we know how to connect a fast and slow model, how about we connect network model with other modalities? Yeah. And that can be served for some well-being purposes. Here, let me introduce AMIR. In connected environments like smart homes, smart cities, smart factories, we oftentimes not only like seeing network traffic, but also we got a lot of readings from other sensors, such as video, audio, or gyro accelerometer stuff. Yeah. And AMIR is a framework that's trying to do active multimodal interaction recognition. Interaction recognition is just another term for activity recognition, because our scenario is mainly based on the interaction with other IoT devices. So we call it interaction recognition here. So today we're seeing many activity recognition using video as a modality. People deploy camera at home for elder care, children care, or even pet care. Yeah. And they also have surveillance cameras facing their living room, back door, or backyard. Because of that, they can also do like home automation. And all this can be put into, for example, like a smart building, smart factory kind of setting. Like home automation can be the factory automation based on like the video input. And these video classifications are pretty brittle because two major reasons. One is statistical failure. Super hard to generalize across all the different scenarios, like activities, different users, different environments. These often have a very long tail. And the fundamental drawback of using video is that they require line of sight. If a person or an object is not inside the frame of the camera, you cannot make any analysis on it. So problems like occlusion, obstruction, different camera angles, and backlighting, they will all make the performance of video classifier worse. So we asked ourselves one question: how do we augment such like powerful but kind of brittle video activity recognition with alternate data? As networking researchers found that there are many IoT devices around, and they are in our smart home. Me personally, I have like 20 different devices at home, and our interactions with these network devices actually generate some traffic that complement with video for some kind of like recognition time. So here is me trying to enter our IoT lab. I'm opening the door of our smart fridge. And on the right side, this is traffic volume. It has a very close correlation, and they have basically quite unique pattern together. Because of that example, and also like we see this general correlation between network and video, we actually see like a very good marriage between video and network traffic. Capturing network traffic is very, it's not super, it's an easy task because it does not need special licensing hardware. We already have routers at most of our households, right? And so it's more ubiquitous than many of the other sensors. And also, it provides us this cyber perspective that is pretty agnostic to the physical arrangement of interaction objects and stuff. So it can be generalizable across different environments. Videos, however, they can be generalizable maybe across different brands of devices, but they will be affected by different users and environments. In order to investigate more, we collected this data at our IoT lab with over 2,000 pairs of collection. And we also have a router and stationary camera at home. We collected traffic from 5 representative devices and 18 different activities. So the first message I want to convey is that network is actually quite reliable when physical surroundings change. So here on the left side, we have like this model being trained in lab or at home, and then they're tested at the same environment or a different environment. As you can see, this video classifiers. When we change the environment, their F1 score essentially drops. For network, though, it's not dropping that crazy. It will stay quite strong. Now that we know, like, basically these are a good match, how about we combining these two models? But combining two models is non-trivial, especially when a lot of times the video models are already pre-trained. There is no reason why people are training the video model from scratch at the day of like 2024. You already got a lot of good pre-trained models, right? And essentially with two pre-trained models, like there are also more and more network traffic models being open source. And how do we combine two models together to arrive for certain activities? Some people would say, okay, how about we just concatenate all the features at the very beginning? However, in order to intake this like shape of features, we essentially need to retrain a uniform model. Even worse, to retrain it, we just need all the collections to be paired, and that process is super costly. How about we just take the output of two models, and then we try to vote by weight. However, if one, even just like one class is failing, like the overall activity prediction will be super biased to one of these predictions, and it fails when one model is broken. A better approach might be just like taking the probability vector out of these two models, and then concatenate them and train a third model up, so that the third model is able to figure out what's the best way to combine these two modalities and two results again. This will need some paired collection for this stacking model. Maybe this is the way to go, but is it the end? Yeah. We want to take one step further, and we want to collect the least possible amount of paired solutions. So we design AMIR for that purpose. The idea is that paired collections are most valuable in clusters where both models are uncertain about their prediction. So still, like we are using uncertainty, is very interesting metric. And the process is basically like this. We have two models, and it needs some validation pairs from any environment because we already tested it. It's basically like it's transferable across different environments, like the kind of stuff the mirror needs. And this validation set, because it can be from any environment, so we already collected that for you. So that can be useful. And if it's outside the scope of the activity, like any lab environment can collect this validation state. So for the first class of all the paired observations, you can basically pass through different models, trying to get the uncertainty from them, and then average them out to be one entry of the final uncertainty vector. For the second class, we do the same. Basically, pass it through, average them out, and have it as a second entry of the uncertainty vector. For the last class, it's the same. After we get this uncertainty vector, now during the first batch of, for example, 10 collections, we will bias our collection intentionally to the most uncertain classes. That's it. Yeah. So essentially, we collect like 5 for class 1, and that will help the static model to learn the best combination of combinations of two modalities from two existing models. So this uncertainty-based collection with AMIR is very efficient. Oh, go ahead.
Can I ask one question?
Sure.
I'm wondering if average is the optimal rate. If you think about it, generally the input tends to be much accurate, and networking tends to be much unreliable. So,
it's not really always the case.
oh,
And,
it's not always the case.
yeah, and basically, like network and video, they have their different benefits. Like video are pretty, it's not very robust against like surrounding changes, physical environment changes, user changes, and stuff. So yeah, under those cases, that's like where the network might give you more signal, and there are different types of activities that's going on, and sometimes that's like video are better than that. But yeah, if we can have like a weighted way to combine these two, that could be better. But that's another layer of configuration there. I guess like that in order not to lose some generalizability, here we're just like simply doing this averaging out. So we found this like AMIR is kind of like a very efficient way compared to baseline, especially of the random and prioritize using F1 Essentially, we are able to collect 120 pairs lab samples and also achieve like 5% better F1 score because of this. So some takeaways for this work. Network traffic is reliable when physical surroundings change, especially for activity recognition. Stacking is probably the way to go to have efficient combination of two models. And the AMIR helps to combine two pre-trained models together with fewer pair samples and achieve better performance. So in this work, we are basically showing how to combine two modalities together. The previous work, we are showing how to combine fast and slow models together. That's what I mean in my title, Connected Machine Intelligence in Operation. Essentially, we're saying like there are many pairs of machine learning models. They can collaboratively achieve some tasks together. And I'm trying to build some like foundation in this direction together with these different works. Going back to this slide, I have all this like interesting, maybe just to you, topics. If you are interested in that, feel free to come to me and we can discuss for half an hour. Just like hanging around in the afternoon. And I'd like to thank you for your attention, and I'd like to take questions here.
Thank you very much. Guys, questions? Any questions? Actually, I have a question, right?
Sure.
So we have a very similar sort of problem to and it's actually dealing with beamforming. If you look at, for instance, in the wireless systems, one idea of improving performance of beamforming is to sort of use the video in addition to feedback or whatever other mechanism to create beamforming or beam tracking.
Yeah.
To use video to sort of augment or help.
Yeah.
And of course, you can have similar things where people use GPS and other things. it's not clear how one would apply a combination, say, of a traditional beamforming things with, say, machine learning based on video.
Yeah.
So do you have any ideas on how to do that?
Yeah. I think video is definitely a good approach to observe like the surroundings, have some physical understandings of some structures around, so that it will be helpful for beamforming tasks. And I'm not so sure how to combine two traditional approaches together. But if like any of these is taking like an ML modeling approach, like two models can try to understand the surroundings together. And if they have some cases that's like both of them are not confident about, we can have this active labeling process on their performance and help to like fuse them in the most effective way. Yeah, and that's a direct implication from the AMIR work. And yeah, I mean, for more traditional approaches, maybe there's often a way to best calibrate their waves, and how do they combine maybe in a more context-aware approach. Like, yeah, on the different approaches, maybe we have different ways on those. Yeah, I would say that's like more environment-dependent kind of approach.
Anybody else? No, but thanks again.
Thank you, everyone.
Thank you.